Welcome to our presentation on Scopos, a free and open source API monitoring tool. We are a team of 4. I'm Elde, and I'm here with my teammates Katherine, Ebel, Gagan, Sapkota, and Nykaela, Dodson. So first, what is Scopos? In short, Scopos is an open source API monitoring tool designed for multi-step testing, API workflows, and running multiple tests in parallel. Before we get too deep into Scopos, though, we're going to start out with an introduction to API monitoring. Then we'll take a look at some different approaches to API monitoring before moving on to some existing API monitoring solutions that we considered before building Scopos. Then we'll introduce Scopos and take a quick look at how to use it. Then we'll explore how we built it, starting with how we built our core components, then diving into our core infrastructure. Finally, we'll wrap up by sharing some future work we'd like to do on Scopos, and at the end, we'll take questions. Okay, so we start with the first section, Introduction to API Monitoring. In this section, we'll explore 2 things: the consequences of API failures and core functionalities of every API monitoring tool. But first, what is an API? APIs are at the heart of every piece of modern software in use, and they act as the connective tissue that binds together application services. Consider a weather application. When a user clicks a button to check the weather in Seattle, the weather app sends a GET request to the weather API. Next, the weather API sends back a response with the requested data. In this case, that's the current weather in Seattle. The weather app then uses that data to display the current weather to the user. It is common for an application to rely on multiple API endpoints. Though, if APIs are central to modern applications, then what happens when they fail? When one API fails, other dependent APIs may fail too. These cascading failures can have unfortunate consequences. Let's take a look at one example where an API failure had a noticeable impact. In 2019, Uber Eats customers were able to order huge amounts of free food because one of Uber Eats payment services, Paytm, changed one of their API endpoints. Before the change, the endpoint returned the same response every time a customer placed an order with insufficient funds to pay for the order. In other words, the endpoint was idempotent. Uber Eats could expect the same result no matter how many times they made the same API call. After the change, the endpoint was no longer idempotent. After the first attempt to place an order with insufficient funds, on subsequent attempts, the Paytm endpoint returned a new, unexpected error message. Now, because of the way Uber Eats had integrated their application with Paytm, this unexpected error message allowed these orders to go through, even though payment had not actually been processed successfully. Before Uber Eats realized the error, many customers had already ordered thousands of dollars worth of food for free. Clearly, it's important to identify issues like this as early as possible, if and when they occur in production. Fortunately, API failures can be traced. And when APIs fail, their failures manifest really in just a few different ways. Maybe, like we just saw with Uber Eats, the data payload sent back in the API's response is something unexpected. Or maybe the failure shows up as an unacceptable response time. Say you need a response back in under 400 milliseconds, but it's taking 3 times that. Or maybe the HTTP status code is wrong. If you need a status code of 200 OK, and you're getting back 500 internal server error, something's probably wrong. So now that we know what to look for to detect API failures, what do? Well, to catch failures as quickly as possible, companies invest in tools that track the performance of API endpoints and look for these signs of failure. These tools are called, appropriately, API monitoring tools. API monitoring tools detect API failures by making requests to endpoints at specified intervals and checking the validity of their response data. What do we define as a failure? Well, whenever there's a mismatch between expected response data and the actual response data, the endpoint is considered to have failed. And by response data here, remember we just discussed three aspects in particular of API responses that we can track: data payload, response time, and status code. But how do API monitoring tools do this? We think it's helpful to think of how API monitoring tools work in the context of a set of core functionalities that are shared by pretty much all API monitoring tools. These core functionalities can be broken down at a broad level as a series of distinct steps: definition, execution, scheduling, and notification. An API monitoring tool allows users to define tests, execute those tests on a schedule, and notify various targets when the tests fail. Let's explore what each of these steps typically looks like. For defining tests, a user provides the information necessary for communicating with the API endpoint. This might include the HTTP method, endpoint URL, headers, and request body. A user then defines assertions to compare expected and actual responses. So an assertion is how a user actually specifies what status code they expect, what response time is reasonable, or what they expect in the response body. Definition functionality is generally offered either through a graphical user interface or a command line tool. So now that the tests are defined, an API monitoring tool has to execute the tests. This means that the tool must be able to send requests to the specified API endpoint, receive response, and check assertions associated with that test against the received response. The tool must also be able to schedule tests to run. And scheduling here doesn't just mean time-based scheduling. It can also refer to arranging for tests to execute from different geographical locations, or setting a deployment trigger to execute tests as part of a CI/CD pipeline. For instance, tests scheduled based on time can be set to execute every minute, every 15 minutes, every hour, depending on the use case and how quickly API failures should be responded to. Finally, when APIs return unexpected responses, the monitoring tool must be able to alert interested parties about the failures. This could include internal notifications that alert self-healing processes, or external notifications to users of the monitoring tool, such as via SMS or Slack. Now, while API monitoring tools have these core commonalities, they are not generally one-size-fits-all products. And these functionalities, definition, execution, scheduling, and notification, can be fine-tuned to suit different use cases. Knowing which features to target with an API monitoring tool depends on which approach to API monitoring makes the most sense for that specific use case. With that said, Kathy is now going to discuss some of these different approaches to API monitoring.
Thanks, Hans. While not an exhaustive list, we identified 4 approaches to API monitoring. Let's take a look at each of these approaches. First, let's take a look at multi-step tests. These tests are designed to simulate complex workflows that consume multiple APIs. Consider a user workflow like the one on the slide: adding an item to a cart, making a payment, scheduling a delivery, and updating the database. When all these steps work as expected, the test passes. However, when one or more of these steps do not work as expected, for example, the payment step fails, then the test would fail. Another approach is parallel tests. Although it's necessary to simulate multi-step workflows by running tests sequentially, this has the disadvantage in that it takes extra time. For example, executing 3 tests that take 200 milliseconds each would take 600 milliseconds. Meanwhile, the same 3 tests sent in parallel would only take 200 milliseconds. Executing tests in parallel can save time when the requests don't depend on each other. Furthermore, making parallel requests can also be used for load testing, because you can configure multiple tests to make a request to the same API endpoint in parallel to see how the endpoint performs. Next, we have geolocation-based tests. Applications with global users may want to test the performance of their APIs from various geographical locations. This approach provides insight into how an API is performing for varied users that are distributed across the world. Finally, we have CI/CD integrated tests. Some API monitoring tools also allow integration with CI/CD pipelines. This is often done by linking tests to multiple environments and setting deployment triggers that run these tests in response to new builds. This practice helps to ensure the API integrations don't break during frequent code-based changes. In summary, the approach chosen to monitor APIs will depend upon the use case. Whereas one company may prioritize geolocation-based tests, another might want to prioritize integration with their CI/CD pipeline. Next, let's talk about the specific use case for our requirements and the use cases existing tools may be used for. We wanted an API monitoring tool that would allow us to monitor multi-step API workflows and execute groups of tests in parallel. The tools we looked at each fulfilled a subset of our requirements. Let's start off with Newman. Newman is a CLI tool for Postman and allows setting up multi-step tests that can run in parallel. However, it has a steep learning curve. Newman requires a developer to write their own test scripts. Also, collections have to be created in Postman and then exported to be used in Newman. Next, we have Checkly. Checkly has an easy-to-use GUI. However, implementing multi-step functionality requires a developer to write their own setup and teardown scripts on each test. It also did not have the ease of use we were hoping to provide. Finally, we have Testfully. Testfully came the closest to satisfying our requirements. However, it locked key parts of its functionality behind high monthly subscription costs. We wanted an open source solution. Ultimately, we did not find a great fit for our use case, so we set out to build our own. Introducing Skopos. Skopos does not include functionality for CI/CD integration or geolocation-based tests. Skopos would also not be a good fit for users who want to have flexible scripting. Skopos, however, is open source, has multi-step and parallel test functionality, and offers a user-friendly GUI that meets the needs of our use case. Let's continue by doing a quick demo of how to use Skopos. To define multi-step tests, a user can click the Add Collection button to create a new collection. From there, they can add a test to the collection by providing details on where to send the request and adding assertions about the properties of the response. For multi-step tests, the user can add additional tests, which can refer to a previous test in the collection by its step number. After all the tests are defined, the collection is ready for execution. To execute the test once, our user can click the Run Collection button immediately to receive the results. To execute the tests on schedule, our user would create a monitor and specify how often the tests are to be executed and how they would like to be alerted when one of the tests fail. Users can choose to be notified by email, Slack, or PagerDuty. If a test fails, Scopos immediately sends a notification of the failure, which includes information regarding the test that failed. You've now seen how to define, execute, schedule, and notify using Scopos. In the next section, Nykaela will discuss how we implemented the core functionality of our application.
Thank you, Kathy. All right, now let's take a look at building the core components of our application, specifically how we built the definition and the execution components. We knew we needed to build the definition functionality and that we wanted to provide a way to set up multi-step tests. An important part of this is referencing values from previous tests. This was challenging because those values are not accessible until after the previous test has completed. For example, if the red fish above wants to know the color of the orange fish, the red fish will only know its color after the orange fish swims by. We also noticed we were working with a large amount of data. Storing and retrieving that data quickly became a complex challenge. Let's look into the first challenge and how we reference values downstream. We decided to group tests that reference previous values from other tests together into what is called a collection. A collection is a group of tests. This way, when the tests within a collection are run sequentially, values needed downstream will be available. In this example, a value from the response of test 1 can be accessed by test 2 or 3, but not by tests in another collection, such as tests 4, 5, and 6. Now, how does a test know that the user wants to interpolate a previous value? Well, we decided to create a reference flag to identify where to interpolate values using an @ symbol followed by 2 enclosing curly braces. Here's an example of accessing data from a previous test in the same collection while using Skopos. Step 1 retrieved an API key that is used here in step 2. You may also notice the reference flag where the @ curly brace is used for interpolation. This is how we solve the challenge of defining where a user wants to access previous values to then be interpolated later on. Now, let's take a look at storing and querying our data. During development, we started by working with REST endpoints. However, those became limiting. Sometimes we were not getting all of the data we needed from one endpoint or underfetching, and other times we were fetching more data than we needed or overfetching. First, we tried to adjust our queries to target the specific data we needed. However, queries started growing in complexity, and the custom endpoints we used started to move away from proper REST implementation. So we decided to use GraphQL. Using GraphQL allowed us to retrieve the precise data we needed, no more, no less. In particular, we added Apollo server to the backend of our application. Any components that would need to communicate with the database could then use Apollo client, and the backend running Apollo server would act as the single gateway to the database. This was a great start. However, while implementing our data model, we ended up making frequent updates to our schema. To mitigate this issue, we decided to use Prisma. Prisma is an object relational mapper, or ORM. It allowed us to not only interact with the database as if it were an object, but also update and migrate our schema with ease. Here's our final data stack, which consists of Apollo client communicating from the front end, a backend running Apollo server integrated with GraphQL and Prisma that then communicates with our Postgres database. Next, let's take a look at our execution functionality. One core problem we faced when implementing the execution functionality, where we are actually making API calls, came with handling the complexity of the code. We decided to group this functionality into what we call the collection runner. Here are the steps for making that possible. Initially, a post request is sent to an express endpoint on the collection runner. Next, data for the tests, including requests and assertions that belong to the collection, are fetched from the database. From here, the process of actually sending requests to API endpoints is started. For this, the requests are first processed by interpolating values the user has defined in the test. This is where our @ curly brace reference flag for accessing values from previous tests comes in. Then the first request is ready to be sent to the specified API endpoint. Once a response is received from the API, assertions are checked for the test. If they fail, interested parties are notified. However, if the assertions pass, the process is repeated with the next request. After this process has been repeated for each request in the collection, the execution phase is complete. As you can see, this requires complex logic and keeping track of variables that change at different parts of this process. Because of this, we started looking at implementing a state machine to run collections. So what is a state machine? A state machine helps declaratively model application logic. It defines states an application can exist in and the actions that take the state machine from one state to another. State machines also keep track of context. As you can see on the light blue clipboards, the values saved to the state machine's context can be updated by different states. We decided to use this and began moving our complex execution logic to XState, which is a library for creating and using state machines. The process begins in the same way we looked at previously, with our collection runner's express server receiving a post request with collection ID as a parameter. From there, the express endpoint invokes our main collection runner machine. As you can see, the collection runner machine has 6 distinct states. At this point, the machine moves from the idle state to the querying state and saves the collection ID to its context. In the querying state, Data for the collection is fetched from the database and, again, saved to the machine's context. The collection runner machine then moves into the initializing state where collection run ID is generated. That will be used to later save the results to the database. From here, each test that belongs to the collection uses a child state machine to handle the logic of processing the request, sending the request, and making assertions on the response. Here's a little more detail on how that works. When the collection runner machine reaches the running state, the request processor machine is invoked. Here, we interpolate values for tests that reference previous requests. Now, this state machine has its own states and context, and when the request processor machine reaches the complete state, the context is sent back in an event to the parent machine. Here you can see that the requests in the collection runner machine's context have been updated based on the data sent back from the request processor machine. Then the request runner machine is invoked, which makes a request to the specified API endpoint, waits for the response, and passes the data to the parent machine to be saved as responses. Once those responses are saved, the next child state machine is invoked. At this point, the collection runner machine has all the information necessary for checking assertions against the saved responses. The assertion runner machine is invoked, which uses the API's response to evaluate assertions defined for the current test. Assertion results are then saved to the collection runner's context. Now, let's take a moment and look at how we handled failures. You may have noticed that each state machine includes a failed state. If an assertion does not pass or an error occurs at any point during a state machine's invocation, the parent collection runner machine is notified and enters the failed state. Similarly, if the collection runner machine does not receive an event from a child state machine, the collection runner machine will enter the failed state. At this point, the remaining tests in the collection will not run and an appropriate error message is sent to any interested parties. Now, this process repeats until all tests in a collection have been completed. At that point, the collection runner machine moves to the complete state and the collection run is done. In summary, the collection runner receives a post request with a collection ID and invokes multiple state machines that go through a sequence of states to complete the tests in a collection. This process allows for the implementation of multi-step tests while organizing the complex logic that comes with that. At this point, we had implemented a large part of our API monitor's definition and execution components. With this, Scopos is able to define and execute multi-step tests, but is unable to perform parallel testing, scheduling, or notifying. We decided to solve most of these problems at an infrastructure level. Gagan will walk us through our cloud infrastructure.
Thank you, Nykaela. We are now going to discuss how we build the cloud infrastructure. In particular, we will discuss how we implemented parallel testing, scheduling, and notification. In the next slide, I'm going to show a diagram of the full architecture. Don't be alarmed. It will all make sense by the end. We're just taking a brief glance at what the final product will look like. Here it is. It might be too complex to parse at the moment, but we will build this piece by piece. Let's break this down into simple components. As you might remember, every API monitoring tool needs 4 key tasks: define, schedule, execute, and notify. We're going to build a full architecture starting with this simple diagram. Now, let's take a closer look at how we moved the definition component to the cloud. We stored the front-end build file in an S3 bucket. We hosted the backend on a Docker container on an EC2 instance, fronted by an elastic load balancer, and we used RDS for our database. Before moving to the cloud, the collection runner was already able to execute multi-step tests. We also wanted to execute the test in parallel. Let's do a quick recap of the problem we set out to solve. Suppose we want to monitor 50 collections every minute, but executing all the tests in one collection takes around 10 seconds. That means executing all collections sequentially would take 500 seconds. If I'm getting my math right, that should be just above 8 minutes. We set out to solve this problem by executing collection of tests in parallel. So we needed a way to run multiple instances of the collection runner in parallel. We could accomplish this in two ways. We could take the single tenant solution or the multi-tenant solution. Let's go over what these terms mean. As you can see on the left side of the diagram, each tenant gets a house. As the diagram illustrates, single tenancy means running one server on one machine. As you can see on the right side of the diagram, 3 tenants share a house. As the diagram illustrates, multi-tenancy means running multiple servers as distinct processes on the same machine. For a single tenant solution, we would provision multiple virtual machines, each hosting its own collection runner process. Then we would add a load balancer to direct traffic to available collection runners. This approach would enable parallel testing for our needs. However, this solution has some downsides. First, provisioning and managing each virtual machine adds complexity. Second, we would be wasting resources. The collection runner is a relatively lightweight process. It would not utilize the full resources of even the cheapest Amazon EC2 instance. In other words, single tenant solution would be quite wasteful. We still have the other option though, multi-tenancy. Containers are the perfect solutions here. To implement this approach, we could run multiple instances of the collection runner on Docker containers, and multiple Docker containers could reside in a single machine. Then, to enable parallel testing, we only had to use a load balancer to direct traffic to different containers. Since the single tenant approach is wasteful, we decided on a multi-tenant solution. We could implement the multi-tenant approach in two ways. We could use AWS Fargate, which is a serverless container service managed by AWS, or we could use Elastic Container Service with EC2. Let's consider Fargate. Fargate abstracts away the complexity of managing virtual machines. AWS dynamically scales the Fargate instance depending on the demand. But we found two main drawbacks to using Fargate. First, Fargate's auto-scaling can take up to 15 seconds to spin up new containers, which would increase compute time. Second, Fargate was a pay-as-you-go service. Since the collection runner makes multiple HTTP requests and waits in between to receive a response, using Fargate means paying for all the time waiting for a response. For our needs, a better solution was to run containers on EC2 instances. That way, we would be paying for the machine rather than the compute time, which would be cheaper. Each EC2 instance could house multiple containers. Although we would still need to provision and manage virtual machines, we could use those resources more efficiently. In this way, we solved the problem of parallel testing. Overall, the solution is as follows. We hosted multiple instances of collection runners in Docker containers housed in EC2 instances and used a load balancer to direct traffic to different containers. At this point, we had both the definition and the execution component in the cloud. Now that the collection runner was set up to execute multi-step tests in parallel, we moved to implementing scheduling, for which we considered two options. We looked at cron jobs and AWS Event Bridge. The first option was to run cron jobs from a Node.js process. This approach would not require any additional infrastructure because the cron job logic could be co-located with the backend. This approach, however, would have significant drawback. Coupling functionality like this introduces a significant vulnerability. If the node storing the cron jobs were to go down, a scheduled task stored on that node would be lost. Since cron jobs introduced vulnerability, we then considered AWS EventBridge. EventBridge is a serverless event bus that can receive and route events based on user-defined rules. And these rules can include cron expressions. We could use cron expressions to trigger events on schedule. Although using EventBridge as a component to our architecture, it decouples scheduling functionality from existing processes and prevents a loss of data from potential failures. Because our aim with Scopos was to provide a reliable API monitoring tool, we decided to use EventBridge. At this point, we started implementing the scheduling functionality with EventBridge, but we found that the EventBridge communicates over HTTPS. The collection runner, however, communicates over HTTP. This meant either we had to acquire and manage SSL certificate for the collection runner, or use an intermediary between the EventBridge and the collection runner. We opted to use a Lambda function as an intermediary. This way, the EventBridge communicates with the Lambda, which then sends a request to the collection runner. At this point, Scopos was able to define tests and execute them on schedule. For notification, we chose to use AWS Simple Notification Service, or SNS. SNS has an effective setup for sending notifications to various services, such as PagerDuty and email. When setting up a schedule, backend would create a topic and subscribers for the schedule. PagerDuty and email links would be subscribers to a topic corresponding to the schedule. When some of the tests fail, the execution component would publish message to the SNS topic, and the subscribers would receive the message. We also wanted Scopos to send notifications through Slack, but sending notifications to Slack requires a specific data payload that SNS could not accommodate. So we chose to send notifications to Slack directly from the collection runner. When the execution component publishes a message to SNS, it would also send a notification to Slack. At this point, Scopos was able to create collection of tests, execute those collections on a schedule, and notify the interested parties when some of the tests fail. Let us now do a quick overview of the AWS infrastructure. Let us focus on the box that the arrow points to. The front end built on React is hosted in an S3 bucket. It communicates with the backend with Apollo server hosted on a Docker container and managed by ECS. The backend communicates with the Postgres database hosted on RDS. The collection runner, which you can see at the bottom of the diagram, is hosted on Docker containers running on EC2 instances and managed by ECS. Frontend communicates with the collection runner to execute tests on demand. Collection runner communicates with the backend to fetch the collection data. Next is the scheduling, hosted on AWS EventBridge. Backend server communicates with the EventBridge to create rules for each schedule. The EventBridge triggers the Lambda that communicates with the collection runner. In this way, collection of tests are executed on schedule. And finally, notification is implemented with SNS. When creating a schedule, the backend also communicates with the SNS to create topic and subscribers. When some of the tests fail during execution, collection runner publishes a message on the topic and the users are notified of the failure. This completes the architecture of Scopos. Next, we will briefly discuss how we would like to develop Scopos in the future. We'd like to do three main things. First, we'd like to implement a sandbox environment to run API requests in isolation for troubleshooting. Second, we'd like to generate random data for different inputs to test edge cases. And finally, we'd like to implement smart notifications to prevent repeat notifications for the same issue. With that, we end our presentation. Thank you for attending the session. We'd like to now open the discussion for questions.
All right, so the first question is possible to use SNS function. Yes, so the question is asking if it's possible to use SNS to send Slack notifications by modifying it with a function. So another approach that we considered that's a common workaround is to use the Lambda function as sort of an intermediary between SNS and Slack. So the Lambda function would be a subscriber to the SNS topic, and then you would send a post request to Slack that way. We decided to not go with this approach just because at our scale of our project, we thought that it would be more efficient to send a request directly from the collection runner, but that's definitely something that would be helpful to decouple if you were to scale our project in the future. Let's see, any other questions? Okay, so there's a question that came in. Were there any other things you implemented in Skopos that you would like to talk about? I think, let's see, we implemented Skopos using the AWS CDK, and that brought about a lot of challenges like circular dependencies that we ran into and things like that, were really interesting challenges to kind of tackle as we were moving to the cloud. Does anybody else in the group have different pieces they'd like to speak about?
I think the main other challenge, like you said, was working with the CDK and initially getting everything up and running on the cloud. Lots of time spent on that.
What was your favorite part of the project? I think the state machine was my favorite part of the project. I think that was really interesting to learn about and try and implement. But let's see, does anybody else have their favorite parts of the project?
State machine was my favorite part.
I just like the whole project, like to combine just like the interaction of all the different components together, and just brought about a bunch of like fun like debugging problems. I don't know if some people consider that fun, but I do. But just like all the pieces working together and trying to figure out how to get them all talk to each other and whatnot was really fun for me.
Yeah, that was mostly like the overall project was pretty amazing in terms of the journey, learning so many things on the way, especially working with the state machine and trying to puzzle through the logic of it. And although it was a nightmare kind of getting it working with AWS CDK was also pretty fun because it was kind of challenging and yet rewarding when it worked.
Yeah. Let's see, how did you decide on what you would make together? So we were really interested in microservices and kind of how the different pieces of those architectures fit together, especially whenever they're so complex, just making sure that everything's running smoothly. And we were kind of looking at observability. And then we were pointed towards Testfully, which is one of the API monitoring tools that we looked at. And from there, started diving a little bit deeper on API monitoring tools, what they're used for and everything like that. So that's kind of how we got started. So through the course of working with API monitoring and parallelization, were there any takeaways regarding test optimization that you'll apply to your future work? This was something that was really interesting. We worked on trying to have tests run in parallel for a little while and considering different options. I think that it was interesting because we needed to decide how to group tests together because we really like the idea of multi-step tests, and simulating those workflows that might require requests to multiple API endpoints, but then we also didn't want everything to be running, one at a time, one after the other. So it was interesting to think about how to group things that weren't dependent on one another, and which aspects we did want to be dependent on one another with the multi-step. So yeah, I think being able to visualize those two differences was really interesting that hopefully we'll be able to take into the future.
Yeah, and I think it was a great experience to get to work with the different AWS container services. I feel like that will be applicable in the future to different sorts of projects, ECS and Fargate and those sorts of services, and really diving in there and figuring out what would be the best solution for running those tests in parallel.
Yeah, to add to the optimization, we were considering adding caching to the collection runner so that if a collection is scheduled to be monitored every minute, it would be kind of wasteful to fetch data every minute. So we're thinking of adding caching at that level. But the problem was with cache invalidation. If the user modifies the collection in between after scheduling and then goes on to modify the collection, the caching would kind of create problem for the updated data we wanted. So we kind of postponed that discussion for later. We're like, okay, once we figure this out, we'll implement this later on. But that's another one that we could consider in the future.
Yeah, all right. Next question was, what was it like working on a team? Hopefully an answer from each of you. Personally, I had a great experience working on this team. I'm thankful for the hard work put in by everybody up here with me. So yeah, I had a great experience working on this team. Anybody else want to?
Yeah, it was great. It was great. I mean, the best thing was like people kind of jumping in to help each other when things kind of life happened, like I had to take one day off to celebrate one of my Hindu festival, and then kind of my teammates pick up the slack, and that was amazing having your teammates kind of have your back. That was nice.
Yeah, it was a fun experience. It was definitely new. It's very different from working individually. We started out pretty rough on planning and coordinating the work, but as we went, we got pretty comfortable with that, and by the end it felt like we were kind of a finely tuned machine in that regard. So it was an interesting growth experience.
Yeah, I also really enjoyed working on this team. Everyone was very supportive and very helpful. It seemed like we had our different strengths that just really made the team work well together. So I thought we all worked really well together, and it was a good experience.
Yeah. Let's see. Did you consider any other cloud providers versus AWS? We didn't. I think it would probably be a good idea to try and look into the different pros and cons of other cloud providers as well. But we kind of focused on AWS for our project.
We briefly looked for like 10 minutes at Google Cloud, but
yeah,
settled on AWS pretty quickly.
Mm-hmm. What was the time breakdown between working on the front end and back end? I think so. The back end had a lot of GraphQL that we were working on because that was kind of our gateway to the database. And so we definitely spent quite a bit of time on working on GraphQL queries and everything that communicate to the front end. I know that Kathy spent a lot of time on the front end and adding some additional features to make it more user-friendly. And then we spent a pretty good amount of time on the collection runner as well. So I think between those three was that definitely a couple of weeks. It was probably pretty even though. I don't know, does anybody else remember more of an accurate breakdown of those?
I feel like once we had the back end kind of its base functionality down, all we had to do going forward as we worked on different parts was kind of tweak different queries or tweak parts of it. I know the front end we had, as we got further in the project, we had a number of irritating bugs that we had to keep tracking down in the front end. I think overall we probably spent more time working in the front end, and the back end was kind of, once we had it set up and mostly ready to go, it was able to chug along. So probably more on the front end.
Yeah, and I think we had some unexpected database challenges too, just coming up with our, entity relation diagram and everything, getting that set. So then we had to go back and, once we changed the database, we'd have to, do the changes to the front end, back end, all of that to make them all work together. So
Yeah, just to add for like the front end part, I know we use GraphQL on the front end. We used Apollo client, and it allows you to do like caching, and that saves you from having to make extra requests to the database. So, just trying to get that all coordinated so everything was caching appropriately, and that was a little bit of a challenge to learn how to do and make it work right.
definitely. Any advice you would give to future Capstone students? I think just keep going, trust the process. It's really interesting working on a project and learning so much new information so quickly. And I feel like it was a lot easier to piece together different components whenever you're figuring out how to actually use them rather than just, reading up on them or looking at docs. So it was really cool to actually apply those. So yeah, I think just keep on going and be open to learning a lot. That's pretty cool. Anybody else have advice?
Yeah, I'd say, trust your team. It's a big shift working with a group of people on a project like this. And, you gotta get to know people and learn to work together in a way that you kind of don't when you're going through the core curriculum. So the sooner you're able to kind of put your ego aside and like work together efficiently, I think that'll make all the difference.
How did you distribute the work? I think something that might have been unique about our team is that we all worked on a lot of different aspects together. So we did have people work on different pieces, whether it was XState, front end, database, notification. So we kind of divided those key components. But I think something that worked really well for our group and hopefully is going to be beneficial with just our overall understanding of the project is if there was a bug or something that we needed help figuring out, then everyone was really willing to jump in and, tackle a piece of the project they may not have been the main person working on, but to still try and figure it out and help each other. So I feel like that's how it worked from my perspective. Did anybody else have a different experience or want to speak on their portion?
That sounds right.
Yeah, I'd say that sounds about right.
Yeah, initially the work, we kind of broke up the work based on those initial components of like front end, back end, database, collection runner. And we each worked on kind of a different one of those until it was mostly up and running. And then going forward from there, when we ran into a bug or someone needed some help with something, while like one person might have had kind of a deeper understanding of that component and kind of like felt more ownership over it, we invited like other team members to come over and help us figure out what was going on, not just because we needed help, but because we thought it'd be, like they said, good for everyone to kind of understand every part of the process.
All right. Thank you everyone for listening to our presentation. I think that we can wrap it up.